where we are now is this sort of change in the pace of things. We have developed very simple ideas of what mechanism can do and what we expect to see, whether it be stepwise or whether it be concerted. And we'll use those ideas again and again, but in the opposite direction. And what we want to do first off is summarize what Chapter 8 was about. The homework was just due last night. Most people got it done. Most people did well. The quiz is due Wednesday. There's a sit-down quiz in recitation this week based on the E1, E2 stuff. And that stuff is, I think, manageable because we do the opposite of what we'll do in 9. In 8, what we do is if we start out with something that is stereochemically defined, like an R or S stereocenter in this molecule, we get rid of that stereochemistry in the three-dimensional sense because we go to things that are flat. And the alkenes that we've built were all sp2 hybridized around those carbons, and those things were flat. We do have stereochemistry in the products, but it's a different type. It's around the double bond, whereas the stereochemistry in the starter materials might be this is a wedge or this is a dash, and that made some difference in terms of the orientations of how those groups fell apart. So if you can get your head around that, 9 isn't so bad, except 9 is more stereochemistry and using the stereochemical outcomes to give you a clue as to what happens. So we developed the E2. The E2 was the one that's more useful to us. The E2 is the one in which you use a strong base. And the very first thing you want to understand from that chapter is the difference in what constitutes a base and what's an acid so that you can do the correct things. In this case, we could choose a large base or a small base, and that will have an effect on the outcomes depending upon where the protons can be attacked. And we'll end up with what we would call predictable, irreversible regiochemistry. All right? Irreversible meaning this very powerful, strong reagent wanted to become neutral and dump its negative charge onto bromine. And that's not coming backwards. That's it. So the outcome here is dependent upon the relative heights of the transition states, on the stability of what you're forming along the way on the transition states, and then the outcomes you can talk about Zaitsev or Hoffman. That's the one that's under basic conditions. The second one at the end of last week was the E1, and this is different now because the pH has changed. We've gone from basic to acidic. We should recognize that. Obviously, we don't need an acid up here because that's a good leaving group as it is. Down here, we do. So for the same reasons as the SN1, you have to protonate the OH to make it a good leaving group. Then you get the carbocation, and away we go. The difference really is this. This one is irreversible, not going backwards. This one is reversible, and that then leads to an equilibrium mixture of the products. So as I develop these ideas of how fast things happen and how stable things are, you must recognize that the top one is governed by the heights of the transition states. The bottom one, because it's reversible, is governed by the stabilities of the products. And that selectivity is seen at different places on that reaction profile. That's a big thing in 9 as we start to develop more complex ideas. So if you're okay with 8, we'll move on to 9. Well, why is this important? Addition reactions are incredibly useful. We're going to add things back to an alkene. You might wonder, why on earth, if we just spent all our time taking things out of a molecule to make it into an alkene, why go backwards? Well, the answer is fairly simple. It's useful. And in nature, you can get alkenes. You can get them from crude oil, from different biological places. And we have them as starter materials. So they can be cheap and they can be used. So we've developed lots of chemistry to go in the opposite direction in which we add. And I bring this guy in. This is Crixivan, which is a complex synthesis by Merck out in New Jersey. 4 of my former master's students work with Merck as pharmaceutical chemists. And the type of stuff they do is build these types of drugs. Okay, either anti-cancer compounds or, in this case, an anti-HIV drug. And the way people go about making this compound, which is quite complex, it's actually a peptide mimic, which you'll see in biochemistry later, is by doing addition chemistry. They have this intermediate, which they've made, and they add things to it. So this example we will see probably later this week, in which we add a halogen and a hydroxyl. That's useful, because then we can close this up to make a 3-membered ring. Those epoxides are very useful. We see a lot of that stuff. And that thing is now spring-loaded and wants to open up because it's strained, and we can bring in a second component and do exactly that. So the starting point is the alkene. Alkenes, you can make them quite easily, and then we can use them, or we can isolate them from nature and use them. So the addition chemistry is the opposite direction. Instead of eliminating now to go flat, we start flat and we add. I think that's more complicated. So if you're struggling with the cis and trans ideas from the earlier chapter, make sure that's clear now, certainly by the end of today, because what's going to happen now is going to go backwards. And what we'll do is start to introduce compounds and introduce reagents that take us back to the 3-dimensional world. That's more complicated because all of a sudden this can be a chiral center and this can be a chiral center. And the identity of those chiral centers as we get more complicated here will help you work out the mechanism. If you get a certain outcome, that must have meant a concerted mechanism. If you get a different outcome, that must have meant a stepwise mechanism. We can use those ideas of stereochemistry to help us work out what happened. So here we go, alkene. A loosely held pair of electrons. You think of an alkene like a lone pair that is shared between 2 atoms. Just like lone pairs can be given away to acids or to electrophiles, we can do the same thing with this pi electron pair. We can push these electrons away to something like X and Y, and you'll find now that the addition can either be stepwise or concerted. Same ideas. Some very simple examples, thinking about how our molecules have many different purposes or many different abilities. You think about this now. You could think about nitrogen in ammonia or oxygen in water. Having that lone pair makes it basic, because now we can go after some proton. So if my double bond is essentially a lone pair shared between two atoms, I ought to be able to do the same thing. I ought to be able to take that pair of loosely held pi electrons and give them away to something that's electrophilic. So we're challenging this double bond with a proton, and the double bond breaks. All of a sudden, we're back into a world that we recognize. Carbocations. What's the best type of carbocation we've got so far, Mr. Haldeman? Tertiary, right? So you prefer to make tertiaries rather than secondaries. Well, that will lead to selectivity. The whole idea now of selectivity in this type of system is going to be based on what type of carbocation can I get when I go in two different ways. Do I get primary or secondary? I prefer the secondary. Do I get secondary or tertiary? I prefer the tertiary. And if I had a secondary cation, what do they tend to do if they can? Rearrange. So if you understand that from the earlier two chapters, this is the same stuff, just going from a different direction. What we'll do now is, instead of just challenging with protons, which we will, we'll also add different electrophiles, different things that aren't protons, and away we go. We'll make a new carbon bond to something else, and we'll end up with a positive charge that again is stabilized by hyperconjugation, and that allows us to go to products. So in terms of energy, in terms of thermodynamics, which do we prefer? Do we prefer the alkene or the thing with all the sigma bonds? Right, so this should be favorable now. There's no problem here in terms of going to something slightly less stable. You're going to something more stable because you went from unsaturated to saturated. You went from pi bond to all single bonds. Now the textbook summarizes this. This is something that you might keep an eye on as we work our way through this list. This table 9.1 is showing you all the reactions that we will have to do involving the addition of HX, HOH, HH, XX, OXX, and OHOH, right? And these are very powerful reagents and ways of putting new pieces into molecules. By the end of term, it's only 5 weeks off now, right? 6 weeks. Thanksgiving's kind of a wash, so it's really 5 weeks. 4 weeks. We've got to think about synthesis. We've got to think about chapter 12, and we chose chapter 12 as the ending chapter for this term because it wraps everything up. It's a nice sort of capstone for the end of this term. You spend the whole time going back and using what you learned in the initial 11 chapters and putting it together to make bigger molecules. By the end of this term, you'll be able to make a molecule from scratch, design it yourself, put it together, and then on paper be able to synthesize it. That's not particularly easy, and it requires you keeping up. So let's get started. We have to think about the process in terms of how fast it goes and in terms of how stable the materials become. What we have done in chapter 8, if I start down here, we started out with this guy on the right. This could have been a bromide, it could have been an alcohol, and we ripped out two pieces. We ripped out some leaving group, and we ripped out a beta hydrogen. And all sorts of rules applied here in terms of regioselectivity, in terms of stereospecificity, stuff like that. And that was the whole point of the quiz and the homework this week. And we can start to think about how favorable this is going in this direction. In chapter 8, we eliminated. And one of the problems here was that we ended up with a pi bond. And that pi bond is stable, but it's not as strong as the single bonds that we replaced. So some of the issues here were based on what are we reacting this stuff with? If this stuff is being reacted with a powerful base, it is the powerful base wanting to become stable that drives the reaction. And the alkene is the byproduct of that. So O minus becoming Br minus drives that process, and the carbon molecule just has to go along. What we did with the alcohols was we said that over here, if this is OH, we need to protonate it with an acid. Then it's a good leaving group, and then you can go to the product. And then we developed this idea in the lab, which we'll do, I think, next week. If you make a less stable alkene, you can drive this equilibrium to the product by getting rid of the alkene. You can distill it away as you go, and you can end up getting a high yield of the alkene, even though, yes, it's technically less stable than what you start with. So you can make this work for yourself. Now, that was the whole point of chapter 8. Now, chapter 9, we don't have any of those problems, because we start off less stable, and we go more stable. So these addition reactions are thermodynamically favored. You'll see why in terms of the bonds being formed and broken, and these are good processes. So everything in 9 now is taking some reagent, adding it to the double bond, and going back to something that's saturated. So let's think about that now in terms of this. So I hope you've been keeping up with this. Some of the online stuff is useful for this, just to make sure you're understanding this. If I'm taking an alkene and HX and I'm producing one molecule, is that favorable or unfavorable in terms of entropy? Unfavorable, right? That's a positive entropy change. If I think about enthalpy, going from a pi bond to sigma bonds, is that favorable for delta H or not? Favorable, right? So we'll find now that there's a battle here between the entropy and the enthalpy. And if I want to minimize, since this is entropically disfavored, I want to minimize this factor, right? What's it going to be? Am I going to be low temperature or high temperature? Low temperature, right? These reactions typically run at low temperature. The elimination reactions are run at high temperature for the opposite reason. So we're going from left to right now in terms of additions. This is worth it. The pi bonds are going to be broken to get to somewhere more stable, and we've got to be very careful here. We've got to consider the whole balance of the equation. Yes, we have a pi bond which is weak, but we also have a sigma bond here that's breaking in the reagent. And in some cases those bonds are quite strong, and in some cases they're quite weak. Overall, we want this to be worthwhile. We want delta G to be negative. So yes, we're taking two molecules and turning it into one, entropically disfavored, but if you keep T low, you don't have to worry about that, as long as delta H is in your favor. And if you're swapping pi bonds for single bonds, it will be. So what we'll start to see are examples like this. No calculations. We're not going to do calculations at all this term. We will do a few next semester, but not very many. We're now going to look at things like the bond energies, which you can get from the table in the textbook, and decide whether this is worth it or not. Well, if you take the alkene, which is worth 63, and you mix it with HCl, which is worth 103, what you get on the other side is material that is more stable. It's worth more energy. Okay? It's more stable. So this is worth it. The delta H component wins, and delta G is going to work. This reaction will work. So any of the additions we do, they might be reversible. We'll see why as we go, but they're all going to be worth it, and the products typically are going to be more lower in energy than the starter materials. Don't worry about numbers until we get to bromine. Bromine, you'll have to worry about numbers, but so far it's just a common sense thing. So here we go. In terms of running these things, you will see, and this will get frustrating because all of a sudden there's no organic exam for a month, therefore I'm doing basket weaving, I'm doing my genetics, I'm doing whatever else I do for my 12 credit hours a term, and I'm not concentrating on organic. That's a bad idea. Keep up with this stuff daily. We now have to think about conditions. Low temperature favors the addition, high temperature favors the elimination, and you will see them compete. In fact, if you go back to the elimination with water, the elimination of a hydroxyl group from an alcohol with acid, we had the forward steps going to an alkene, but now we're going to see the alkene going back to the alcohol. We're going to be able to go in both directions, and we have to learn how to affect that in the lab and make it work. Starting off with hydrohalogenation, the addition of something like HBr, HCl, and HI. Not HF. HF is not a powerful acid in this sense. HF has a positive pKa, and it's not as acidic as the other guys. So HBr, HCl, and HI will do this. And you'll notice now we do run this at quite low temperature. We have started to put detail in because you need to be concerned about detail. We'll see here that if we measure the rates of the reaction, we find that stronger acids go faster, which makes more sense if a protonation is involved. If a proton transfer is involved, the stronger acid should be better at giving those protons away. And we'll find now that HI is better than HBr, is better than HCl, and much, much better than HF. And that just correlates with their acid strengths. The stronger the acid, the faster this process. And that sort of assumes or suggests that a protonation step might well be involved in this reaction. And in fact, it will be. So we're going to add both pieces. The piece that's missing here is the H. The H goes onto one carbon. The bromine goes onto the other. The bromine here is at the alpha carbon. The H is at the beta carbon. The same geography, the same language we used for the previous chapter. So this now is going to cause you some problems because we're going backwards. But again, it's important because we have now entries into different types of compound through doing this. There's an alkene. I've been careful on this slide to make sure that this alkene is symmetrical. So both the carbons of the alkene are the same. You might write that down. This is a symmetrical system. This carbon is the same as this carbon. Obviously, when they're not symmetrical, things will change, and that's where the regioselectivity will come in. What I need to worry about now is this. This is an acid. Acids tend to protonate things. So if they protonate lone pairs on water or ammonia, they should protonate a double bond. The problem is, when you protonate water, it's only oxygen with a lone pair, and you end up with a plus charge. In this example, both of those carbon atoms that I just highlighted, both of those are part of the pi bond. They are both sharing that lone pair. So if I'm making one new bond to a hydrogen, let's say I pick up this hydrogen and I break that bond to bromine and I put this guy on there. I have used up the 2 electrons from the pi bond by making one bond to hydrogen. So the point now is that something has to lose out. One of those carbons has to lose out. Depending upon the substitution pattern in a minute, you'll see fairly obviously which one prefers to lose out, but in this case it doesn't matter because they're both the same. So we form a carbocation. From what you know, and this is where we get good at this, we start to trust what we know. Is that a fast step or a slow step? Be very careful. We're going to a carbocation. What do you expect? Slow. Right? You're going to a carbocation. Yes, it's a protonation, but overall we're going to something less stable, so that should be endothermic and it should be slow. We produce a carbocation. Carbocations need some help. They need to benefit from the presence of something nucleophilic, which is electron rich. And in this case, we have the Br- conjugate base from the acid. This is behaving as what in the second step? A nucleophile, same language. Is that carbocation going to be easy to attack or difficult to attack? easy because it's flat, right? It's flat, so it doesn't really matter here. What we end up with is a saturated material in which the balance of the material on the right is more stable than the balance of the material on the left. So this is worthwhile. And it's not going to go backwards necessarily under these conditions. So far, slow. And I'm going to start doing that. I'm going to start asking you to construct these things, particularly in recitation. You give me the answers, and hopefully it starts to add up. Slow in the first step, fast in the second step. Which one should be rate determining? First step. How many steps in the reaction profile? 2, right? Which one is higher or lower? Which one is the higher one? First one. So even without looking at it, you should be able to draw that reaction profile and start to draw transition states. Transition state in this first step is this pi bond breaking and this H attaching to one of those carbons and this Br breaking off. We will draw them in a minute and you'll see that they're not so difficult. So all of a sudden, with a symmetrical system, it's pretty straightforward. It does not matter where you put the H in the Br or the H in the Cl because you end up with the same product. There's more complication coming up in a minute because you can make chiral centers. But right now, for a simple system like on that previous slide, it didn't matter which carbon I went for because you end up with the same products. Now it gets more complicated necessarily because in nature, bacteria do this. They do addition reactions to produce their own building blocks. We need to worry about geometry. We need to worry about regiochemistry, where things happen. So if you've got your head around the idea of Zaitsev and Hofmann, this is the counterpart. This is going in the opposite direction. Zaitsev and Hofmann were making alkenes. This is now adding to an alkene to make something saturated. And we're going to call this Markovnikoff addition. Markovnikoff and Zaitsev were colleagues, I think, at the same university in Russia. One guy decided to do alkenes, the other guy decided to go in the opposite direction. And this rule now is something that will stick with you, especially in biochemistry and further. If we take an unsymmetrical alkene, that's the key here. This thing is no longer symmetrical. I have 2 carbons in the alkene which are not the same. I have a choice of where to put my proton. I could put my proton on the end, producing a carbocation there, or I could put my proton in the middle, producing my carbocation here. Now, this is the beginning of some very subtle language. We've got to be on top of this stuff to do well here. We will get vastly, that will be the major product, in huge amounts. You might get none of that. It'll be minor, if anything. This is now a discussion about when the selectivity shows up. In the past, with the E2, for example, the selectivity showed up in the transition states. In this case, where does the selectivity show up? Transition states, carbocations, or products? Carbocations, because I'm going to have a choice here. What type of carbocation led to this guy? Tertiary. What type of carbocation led to this? Primary. Which do you prefer? Tertiary. By how much? A lot. So you pretty much get exclusively this stuff. And we've got to be very careful here. I'm going to say this many, many times, as carefully as I can. The selectivity involved in this process is to do with the relative stabilities of the intermediates. Okay? So Markovnikoff addition in this sense will prefer to give you the product that came through the more stable intermediate. That's a general thing. Mechanistically, this isn't difficult at all. It's 2 steps. You protonate, you form a carbocation, then you do a nucleophilic attack, you get your product. Worthwhile because you go from less stable stuff to more stable stuff. But the selectivity involved now is all to do with preferring a tertiary carbocation. So I'm going to write this in. You might put this down yourselves. It's via a tertiary carbocation. This one would be via a primary carbocation. It is not, be very careful here, it is not because this product is more stable than that product. That's got nothing to do with it. In fact, they're not very far away. If you add up their bond energies, they're not very far away. They are certainly not far enough away in their bond strengths to suggest or to explain a 99 to 1 outcome. If you get 99% of this and 1% of that, it's got nothing to do with their relative stabilities because they're not that different in stability. It's got something to do with the mechanism, and the mechanism here is through carbocations, and you much prefer to have a tertiary carbocation than a primary. So what we're seeing now is the first example of Markovnikoff regioselectivity by addition to an unsymmetrical alkene. Are we okay? Right. Here's the graph for the formation of the tertiary cation. I already asked you how many hills there would be. There are 2. Of course, there are 2. Which one would be higher? It should be the first step because it's going to be forming a carbocation. That activation barrier between here and here is much bigger than this activation between here and here. And that should add up. Carbocations are flat. They're easy to attack. There's no problem there. Well, in terms of the steps, proton transfer, you've got to be careful now. Yes, it's a proton transfer, but it's a slow one because it's going to something quite unstable. Be on top of that. Once you've got your head around that particular graph, you can draw some of these guys up here, which I expect everybody to be able to do. we can start to talk about the relative heights of these hills and the relative selectivities. Because what's going to happen now is this. I'm going to start here and go back a second. This is the first example maybe we've seen one before, of two competing processes to give two different intermediates. We saw two different processes with the E2, right? But that was one step. Now we're seeing two different processes to give two different products, starting from the same starting material. That undoubtedly is more complicated. So think about transition states. You are starting with an unsymmetrical alkene, which has a secondary type carbon and a tertiary type carbon, and we're making two products. In this first case, we're heading to the tertiary carbocation. The same rules apply. Tertiary carbocations are preferred because there's more hyperconjugation possible. Look at that transition state. I'm thinking about what changes. This starts to change, and one of those carbons becomes positive. So I need a delta positive on carbon. We haven't seen carbon be much positive or negative so far. Now it's starting to change that. The double bond is starting to break, the bond to hydrogen is starting to form, and the bond to the halogen is starting to break. And since the X breaks off as a leaving group or a conjugate base, it must be delta negative in the transition state. That should be pretty clear. At the top, we have the situation with the secondary system. Now, okay, a secondary cation is not as stable as a tertiary cation. We're fine with that, right? But now we have to start thinking in a more sort of nuanced sense about what is happening as the reaction is happening. What are the changes occurring? Are the changes occurring as you go from this over these hills to these products? So what's happening now is that this carbon on the left, or in this example, this carbon on the right, they are becoming positive. So they will have some carbocation characteristics. They are starting to become positive. They're starting to lose electron density. And it's the same rule. You want to develop electron density or electron deficiency on a carbon that can handle it. So which prefers to handle that, the tertiary or the secondary? Tertiary, the same reasons, right? The same reasons. You've got adjacent bonds to help out. So a lot of the discussion to come up in the next week or so is going to be about what's happening up here versus what's happening on the rest of the graph. Transition state ideas, talking about how high those barriers are, not absolutely fundamentally in terms of numbers, but relative to each other so we can understand the outcomes. I'm going to go back. There's my graph. Here's my mechanism. If you have concentrated acid, this works quite quickly. You have a slow step to give a carbocation, which is secondary. Not as good as a tertiary. If you went in this direction, where you add the proton to the other end of the double bond, you make the tertiary carbocation. So the only difference there, watching that slide, is that in the first one, the proton went to the right. In the second one, the proton went to the left. It's the carbon now you should focus on. What type of carbon are we dealing with? At the top, we have a secondary. At the bottom, we have a tertiary. You'd much rather have the tertiary. So take a time out here. The selectivity here is not to do with the products. The selectivity in the Zaitsev elimination when we did the alcohols was to do with the products, because that was reversible. This tends to be mostly irreversible, so you're not dealing with the outcome of the products, you're dealing with what you went through, the transition states to get there. So in this case, a secondary type transition state enables a secondary cation. In this case, a much better tertiary system enables a tertiary cation, and you are going to prefer this material ultimately as your major product. We'll keep a track of this in recitation. We'll try and do it in lecture, organizing yourselves in terms of what rules govern the outcomes. What are the selectivities about? There's your graph again. You ought to be able to draw those. You ought to be able to discuss why you get more of one than the other. I don't think it's much more difficult than what we've done, but there's more of it. That starts to get quite tricky. Questions? Must have been a heavy weekend. Everybody all right? Okay. So here we go with what I don't like to do, but unfortunately have to do, is having discussed what we call Markovnikoff addition, is then have a brief look at what we call anti-Markovnikoff addition. So it's the opposite sense, and this is where synthesis starts to get quite clever and quite useful. It's fairly obvious why I should get mostly this product in that reaction. I pick up the proton, I make a tertiary cation, it gets trapped, I end up with the tertiary product. Great. That's a very useful method to make that molecule. And if I want that molecule, great, I have a method to do it. But this slide now, I think, is starting to lead into what I think is more complicated in the later chapters. What if your job was to build the compound at the bottom? The compound at the bottom is technically the wrong isomer from up here. It is the primary system. It's the one you're not going to get with the chemistry at the top, because the chemistry at the top goes through carbocations and gives you that outcome. So how do you make this compound? If you want this is part of your drug synthesis, you know, it's there for a cure for something, you need to make this on a large scale so the engineers can go ahead and start producing this stuff. How do you do it? Well, if I simply mix HBr with my alkene, am I going to get much of any of this guy down here? No, it's the wrong product. It looks like it cation through a primary carbocation. That's not going to work. So this now is a transition for you thinking about these ideas. If you want to change the regiochemical outcome, you must change the mechanism. You must change the factors in the mechanism that drive the outcome. You simply can't rely on carbocation chemistry here because it'll give you the wrong isomer. If you want this, great. Carbocations all day. If you want this, no. It's not going to happen through carbocations. So the problem with this part of the chapter is that this has to be said. We're going to learn a method so we can use it, and by the time we get to the final, you'll know exactly what the mechanism is and you'll be able to do it in your sleep. But right now, we don't know enough to cover the mechanism of this. Suffice to say, it isn't the same mechanism as the one above, and that allows for a change in where things happen. It'll be a radical mechanism later in chapter 11, and it will switch the outcome. Okay? So it's not carbocation chemistry, it's something different. And to initiate that and allow it to go, we need to change the conditions. Instead of just adding HBr, which will give us this, we have to add this stuff, which is peroxide. And peroxides are unstable, they break apart to give radicals, and that gives you a completely different mechanism. What you need to know right now is this condition. This condition, or these conditions, give you the opposite outcome to a regular Markovnikoff addition just using acid. It will be very useful soon to introduce bromines. What do you think bromine does in a system? What's its main purpose? It's a leaving group, right? So now we have methods of putting leaving groups in there to go further. And when we go further, you'll see why this is useful. So right now I've got two methods, one of which is carbocations, one of which isn't, one of which will be radicals later on, which you don't need to worry about just yet for this third exam coming up, unless we get there. And we can switch the regiochemical outcome. Starting to get very useful. Okay. Well, of course, it wouldn't be any fun if there wasn't any chirality. Why do we spend all that time in chapter 5 worrying about Fischer depictions and Newman depictions and wedge dashes and all this stuff? Because we need to see it now in reactions. We're bringing everything together, these big ideas. If I do this with a simple alkene, if I add HCl, the mechanism will be identical. It'll be this guy going after this. The chlorine will break off to compensate, as it usually does. We'll form a carbocation. And in this case, what do you prefer? We can get, what type of carbocation comes from this carbon? Secondary, what about this one? Primary, which one do you prefer? So therefore we get mostly that product. Yeah? We'll see now as we work our way through this, if you have a choice between a primary and a tertiary, it's all going tertiary. If you have a choice between a secondary and a tertiary, you get mixtures that are closer together because the heights of those barriers are closer together. But now all of a sudden, we have induced or brought in some chirality. That carbon right there has 4 different things attached. So let's think about the possibilities. Now, what shape is my carbocation? It is flat, it is planar. From which directions might we attack? Both. Roughly in terms of how much comes from this side, how much comes from this side. About the same. So if I make chiral molecules, how do you describe them? Racemic, exactly. We've seen that before, right? You form a carbocation. If it changed, nobody would be able to do this subject. It doesn't. A carbocation gets trapped. It is potentially chiral, so we call it prochiral, and it traps, and you get 2 outcomes which are enantiomers, and that then is a chiral racemic mixture. So watch out for this now. I think this is more complicated because we're going from flat, which is simple, to 3-dimensional, which is more complicated. We're putting chirality into these systems. What would alpha D be for this mixture? Okay, equals 0. And those numbers, again, will be useful as clues to solve problems. When you're trying to decide what's happening, alpha D is often a big clue to decide what happened. Stan, you all right? On your game? Good man. Right, there's the rationale. Take this out of the context of this reaction. It's the same picture we used earlier on. When we did the SN1 reaction, it's the same picture. You're bringing in nucleophile to a carbon which is flat. If it already had 3 different things on, you bring a 4th one in, it's going to change its shape to become 3-dimensional, and therefore it's going to be an enantiomeric to give you a racemic mixture. That's that, yeah? So these additions, when you've got an unsymmetrical system and you can make a chiral center, you're going to get an alpha D of 0. Ready? You can add HX, not HF, but BrClI quite easily to an alkene to make very useful materials. And from now on, you can decide where your halogen is going to go. You have the methods to be able to do that, at least on paper so far. So thinking about this, Markovnikoff or anti-Markovnikoff? Can everybody say Markovnikoff? Say it carefully. Go on. Go on, Alderman, say it. Yeah, stage fright. Oh, Markovnikoff. Right. Is this Markovnikoff or is it anti-Markovnikoff? Or if you're from Boardman, anti-Markovnikoff? What is it? It's Markovnikoff because there's no peroxide, there's no additional reagent. You'll learn that very quickly, that this then gives you outcomes. Now, am I going to get all of one product or should I get a mixture? A mixture. Now, these are problems, right? These are things that people are concerned about. I already had a flood of people in my office this morning asking about homework 8 whether mixtures were a problem. This is key. This is detail. You need to know why these things are happening. What type of carbocations can I generate from this system? Secondary and tertiary. So they're not too far away from each other. You expect to get products that should be mixtures. And the detail now adds up. It's nothing new, but it is sort of adding up from different angles. I get most of this. Why? Be very careful the way you say this. Why do I get most of that? More stable carbocation. That's what I'm after. If you don't learn this to the right depth, you'll say that's a more stable product, which is nonsense. If it is, it's not stable by much. It certainly is not stable enough, more stable than the other enough, to give you this major-minor thing. So that's fine. Why no plus-minus here? Why no wedges and dashes? It's not chiral. It's achiral. And then over here, what's my little squiggly trying to tell you? It's a mixture of both. It's a mixture of wedge and dash. And maybe we haven't spent so much time on this just yet, but plus-minus is a very quick way of saying that. It's a very quick way of writing down this is racemic. Plus means, one isomer goes in one direction in the light box, the polarimeter, and the minus means the other, opposite. The enantiomer goes in the opposite direction. So plus minus there says it's an antimeric mixture. So I'm going to get less of this, not because it's less stable, but because the carbocation going to it was less stable. And now you have a Markovnikoff type system. What's this, Markovnikoff or anti-Markovnikoff? Go on, Haldeman, say it. Oh dear. Fail. Anti-Markovnikoff. You should practice these things in front of the mirror even if people think you're weird. This is going to give you the opposite outcome. The mechanism is yet to be understood, but we're going to go in different ways. I have carbon on the left, I have carbon on the right. Under these circumstances, where does the bromine prefer to go? On the right, it's the opposite. So we should get mostly this, and we should get a little bit less of that. All you know so far is that it's not through carbocations, because carbocations would give you the outcome in the first reaction right there. Again, what does the dash mean? What does the squiggle mean? Racemic, because that is a chiral center. Why not put a squiggle here? It's not a chiral center. Everything adds up. If you're okay with the stuff we've done before, this is just more of the same. Last example, Markovnikoff or anti-Markovnikoff? Markovnikoff. Where do you expect the chlorine to prefer to go? The top carbon or the bottom carbon? Top. Okay. Looking at that system, will you have a chiral center in the major product or not? Okay, be very careful, because if you put your proton down here, that's a CH2, just like a CH2 up there, that's symmetrical. And so it's achiral. Yes, it's the major product, but it's achiral because there's symmetry in that system. Over here, minor product going to the secondary carbon because it came through the secondary carbocation, but we do need a squiggle now because you can attack from the top or the bottom, giving yourself a racemic mixture with alpha D of 0. Everybody happy? Alan.
So even if the Markovnikoff condition you still get
the conditions are different. This is a different set of conditions to this. That peroxide makes all the difference mechanistically. So for
you still get one product that you can't take Markovnikoff.
yes, typically you're going to get one. You're going to get both products, but which one is major switches? That's the key for that. Svensson, you all right? Yes. Well, carbocations wouldn't be any fun unless they rearranged. So of course, if you can do a rearrangement in the SN1 with a carbocation, and you can do a rearrangement with the E1 with a carbocation, you should be able to do a carbocation rearrangement with an addition reaction. So we're going to see that again. We're going to see that this unsymmetrical starter material, adding to HCl, is going to give two different products. But those of you who are awake should recognize that, okay, this carbon is not involved in the alkene, but all of a sudden, my major product involves that carbon. That's the first thing you check. You check to see if there's a difference in the skeleton, and if there is, it had to be a carbocation. I mean, write that down. That's a given. If you're struggling for what the mechanism is, if you see a rearrangement, it must be a carbocation involved, which should give you a clue as to where to go. Well, first off, let's pick this proton up. Now, it seems to me that over here, we don't seem to have a product in which the chlorine ends up over here. Any arguments as to why? Why doesn't the chlorine end up over there in any of our products as it shows? It would be a primary cation, and what don't we like about primary cations? The fact that they're primary cations. Yeah, they're horrible. So we don't need to make them. So the vast majority of this stuff has come about from a carbocation right there. And then that carbocation seems to have rearranged. So let's go after that. There's your protonation step to make that secondary cation. What is going to migrate? I have a hydrogen here, and I have two methyl groups. What prefers to migrate? The hydrogen. Why? Because it will leave a tertiary cation. If you migrate a methyl group, where do you go? Secondary cation. That's no good. So now we have a nice system. There's your secondary cation rearranging. Yes, some of it gets trapped, but we have this intramolecular process where everything is already there. Is that fast or slow? Fast, right? So this step is quite fast. Yes, attack at a carbocation is fast, and this is a fairly fast reaction, but if everything's already organized inside that system for this thing to rearrange, that will also compete and be fast. And what you'll do here is end up with a tertiary cation, which is good, trap with the nucleophile, and there's your major product. So just put an asterisk next to it. Rearrangements are a problem with carbocations. They lead to reactions which aren't particularly reliable. They're not going to give you exactly maybe the products you expect. You just got to be on top of it to recognize when that happens. So you can get, of course, all sorts of things happening. In this first system up here, what information is missing from this carbon? It's chiral. Yeah? It was a secondary carbocation that was prochiral. So to finish that question off, you would also have to put in a squiggle here, because that is a chiral center. So you're getting three products, two of which are enantiomers, and one of which is not. This one is achiral. Complicated. Okay. Anybody got anything to say about that? Michaela's not here, so people say stuff. Cruikshank, say something. Oh. Should have fun with this, Tyler. Right. We're going through a shopping list. But as we go through this shopping list, we get more and more information about what we just did. It should reinforce itself. It should build and reinforce itself. And at the end of 9, if you can get through 9, and you can pass this next exam, you should get through the 2 semesters. Right? I've got 122 left, about 85 of who show up for class. The rest are, whatever. If you get through this next test with a reasonable score, you should get through the 2 terms, because this chapter is the beginning of that really heavy material. It would be useful, and it is useful, if you can take an alkene, which you can buy or you can extract from some source, and you can add water to it, and you can go to the alcohol. Now be very careful. We did exactly the opposite of that in the previous chapter. Chapter 8 was starting with that alcohol. So keep organized, look at the stuff I've got on my website, do this daily so we don't get lost. I'm now starting with the alkene, which I can get cheap, and I'm adding to it to make an alcohol, which may be useful. And this is under the same type of environment as the previous HBr edition. It's acidic. H3O plus, of course, will be a sort of abbreviation for sulfuric acid water. Sulfuric acid dissolves in water and gives you H3O plus. It's a strong acid, and we'll use it. We'll see now the steps of this are exactly the opposite of what we did for the E1 with the alcohol. Absolutely the opposite. And we get a very high yield of this stuff, and we don't have to worry so much about distillations here because the product is more stable. And just like that previous reaction, the E1, this will be reversible. And a reversible process, this is where you've got to listen carefully. In that previous reaction, it was all about the carbocations, right? In this case, yes, it'll be about the carbocations. But in terms of which is favored, this stuff or this stuff, the right-hand side is now favored because that alcohol is more stable than the left. So this reaction goes in your favor. You don't have to worry about playing any tricks here. You'll take alkenes, water as the nucleophile or solvent, and sulfuric acid as a catalyst. So we're going to add a catalyst. How much do you need of the sulfuric acid if it's catalytic? Not very much, because you keep getting it back every cycle of the reaction. Every time you go to the product, you get the proton back, it can react again. You don't need much of it. So this will be catalytic. If you see that abbreviation, that's what it means. It doesn't mean feline, it means catalyst for the biologists. Okay? Right, here we go. Do some experiments, put the flasks next to each other and decide how fast things should happen. Starting off with this alkene. What's the only type of carbocation you can get from that alkene? It's a primary carbocation. So I'm just going to write that over there to keep the track of it. It goes via a primary carbocation. What type of carbocations can you get from this guy? Secondary and primary. Which one do you prefer? Secondary. Now look at that. Through a secondary cation, how much better is a secondary cation compared to a primary? Well, there's a number that kind of tells you. The reaction is 10 to the 6 times faster. So a secondary cation is much better than a primary cation, because all of this height of these barriers, that's what's leading to the carbocation. The height of the barrier dictates how fast the reaction goes. How much better is a tertiary cation than a primary cation? Right there, 10 to the 11. So obviously with those vast differences, we're going to prefer to get this. We can get this, but we're not probably going to get that, if we can help it. And this is where the selectivity comes in. If you have a choice between a primary and a secondary system, you're going to get mostly the secondary. If you have a choice between secondary and tertiary, you'll get mostly the tertiary. If you have a choice between a tertiary and a primary, what do you get? All tertiary. Those ideas now are starting to come out. So this is obvious. The faster is all to do, how fast things go is all to do with the carbocation you're going to. And these will be very simple processes. You don't need heat here at all, and they will work. So let's think about this mechanism, then we'll stop and go to recitation, and then get back into this on Wednesday. My plan is to do about 5 days of this stuff to get through this chapter, and then head towards the end of term. First step, proton transfer. Carbocation gets formed. The difference now is we're adding water, not HBr or HCl. Is that first step fast or slow? You're making a carbocation. Slow. As you're studying, put this one next to what we just did. It's the same thing. You just switched out the nucleophile. It's the same reaction, the same pictures, the same reaction. In the second step, water acts as a nucleophile, attacking that to give this oxonium ion. Fast or slow? Fast, right? Carbocation being attacked, it's flat, water going in. Last step is a simple acid-base reaction in which a proton gets transferred from the substrate to the water as base. Fast or slow? Fast. Start to trust what you know, especially if you pass in the class. You know enough now to be able to make considered statements about whether these things are fast or slow. And it's consistent. So with that in mind, look at the use of water here. What is water behaving as there? What's it behaving as in that process? It looks like a leaving group, right? It looks like a leaving group or a conjugate base breaking off. What's water behaving as here? Nucleophile. What's water behaving as there? Base. See how general it is? See how useful it is to be able to do that? Well, that leads us to some very useful Markovnikoff type selectivities when we add H plus H2O to an alkene. We'll come back on Wednesday and we'll talk about the concentration of the acid. But right now, H plus H2O, which is generated by dissolving sulfuric acid up in some water, diluting it down, will give you addition of water to the alkene. But if I'm adding H plus H2O, I can see where my OH has gone, I can see where my H has gone. What's left over? If I'm using this stuff, H plus and H2O, what's not shown in this picture? H plus, that's the catalyst, that gets regenerated, right? It's not part of the product, you get to use it again. Note the selectivity here for the final thing today. Why am I only getting the one product? It's a tertiary product, so what's the argument? It's not because it's a tertiary product, what's the argument? It's through a more stable carbocation. You want to put your charge there, which is tertiary, and not there, which is primary. So it fits. So have a go at this stuff, see you in recitation, get some help if you need it, and do well.